Okay, so in this second part, we'll consider several applications of the reflection principle that we just proved, and we begin with the following example. Okay, namely, we'll compute the distribution of the supremum of a Brownian motion up to a given time. And right away we notice that if we try to compute the distribution of the supremum, and we'll consider probability of the form that this exceeds some positive level C, then we can rewrite this in terms of the stopping time or the heating time of the level C. So in other words, we can write that this is probability that tau C is less than or equal than B, where tau C is the first time our process hits B. Right? So crossing level C up to time B can be written in these two ways. And then we are going to use the reflection principle in the following way. So this event here can be visualized as follows. Okay, so we can consider this positive level C and also consider this process on the interval from 0 to B. And the fact that this heating time is less than B means that your process will hit or reach this level C before B. So here you have this stopping time tau C, and so it occurred before time B. And after that, we'll consider two possibilities what can happen after the stopping time. Okay, so one possibility is that your stopping time at time B ends below level C. And we'll use reflection principle to consider also that the possibility that if you reflect this around level C, right, that you end up above level B. And we'll appeal to the reflection principle to say that these two probabilities are equal. Right? So in other words, we are going to split the probability that tau C is less than or equal than B into these two possibilities. So the first one is that the increment of the process after the stopping time up to B, so WB minus W at the stopping time, will be strictly positive plus the probability that this increment will be strictly negative. And here I'm excluding the possibility that it's equal to 0, because we'll discuss in a second why that probability is actually 0. And so the reflection principle that we proved says that these two probabilities must be equal. So after the stopping time, you're allowed to put the minus sign in front of the increment of the process after that time. So in this picture, it really corresponds to reflecting the process around this level C. And since these two probabilities are equal, I will write the sum as 2 times the first probability. Okay, so this is the step where we use the reflection principle. But notice now that the probability written here can be simply stated by saying that the process W at time B is greater than C, right? Because if you look at this picture, the fact that the increment is positive means that at time B you end up above level C, but if you know that at time B you end up above level C, by continuity of the process you must have crossed level C somewhere before that time. So you don't need to mention the fact that tau C is less than or equal than B. And of course, this event, it's just in terms of one Gaussian random variable with variance B. So we know that WB, it's just Gaussian with variance B. So this probability, you can write it in terms of the Gaussian density. So in particular, if you rescale by square root of B, to write in terms of standard Gaussian density, you can write this as an integral from c over square root of b to infinity of the standard Gaussian density. Okay, so in other words, we calculated the distribution of this supremum, and at the same time we calculated the distribution for this stopping time or for this heating time. And if you like, now you can take derivative with respect to parameter b or parameter c to find the density of the corresponding distribution. So for example, if you want here, since this probability that we computed is just the probability that tau c is less than or equal than b, if you take the derivative in b, you'll get that the density of tau c, okay, is equal to 1 over square root of 2 pi c over b to the 3/2 e to the minus c squared over 2b, okay, for positive b. Okay, in particular, you can see that at infinity, the leading order is 1 over b to the 3/2. Right, in the exponential, the term goes to 0, so exponential becomes 1, and the leading order is b to the 3/2. So in particular, when you compute the expectation of tau c, you will integrate x times something like 1 over x to the 3/2, which is not integrable. So you get that the expected value of this heating time for any positive c is plus infinity. Okay, so this is an example for a Brownian motion. Then we want to give several examples for the Brownian bridge. And for that we need the following lemma, which explains that you can view a Brownian bridge as a Brownian motion pinned down to arrive to 0 at time 1. Brownian bridge is sometimes called pinned down Brownian motion. Okay, namely, we'll show that if you consider the conditional distribution of the Brownian motion on the time 0, 1, conditionally on the event that at time 1 the Brownian motion is close to 0 or within epsilon from 0. Then when you let epsilon go to 0, then this distribution on the space of continuous functions on 0, 1 will coincide with the distribution of the Brownian bridge on 0, 1. And the main observation in order to prove this is the following: that if you consider some Brownian motion on some probability space and take this specific version of the Brownian bridge, the way we define it as a Brownian motion minus t times the Brownian motion at 1, right? Both of these are Gaussian processes, and if you calculate the covariance between this Brownian bridge and the Brownian motion at 1, well, you can see it will be just the covariance of Brownian motion at time t and 1, which is t, minus t times the variance at 1, which is 1. So actually, you notice that this particular Brownian bridge is independent of the value of this Brownian motion at time 1, right? So bt is independent of w1. And in fact, this is how we will use this lemma below through this observation that this specific Brownian motion is independent of w1. Okay, but to finish the proof of this lemma, then you just notice that when you consider the distribution of the Brownian bridge conditionally on it being at time 1 within epsilon from 0, okay, we can write this Brownian motion as bt plus t times the Brownian motion at 1 just by moving this term to the other side. Okay, but on the right hand side we just check that the Brownian motion bt is independent of this condition. So condition only applies to the term t times w1, and as a result this is the same as the distribution of the Brownian motion plus t times, let me call it eta epsilon, okay, where eta epsilon is independent of the Brownian motion, and the distribution of this random variable is just the distribution of standard Gaussian condition to be less than or equal than epsilon. Okay, so in particular, this random variable is less than or equal than epsilon. Okay, and of course, now when we let epsilon go to 0, the second term is less than or equal than epsilon in absolute value, so you can conclude that this converges, this distribution converges to the distribution of the Brownian motion, okay, on the space of continuous functions on 0, 1. Of course, if you want to make this last claim a little bit more precise, you can just take a bounded Lipschitz function on the space of continuous functions on 0, 1 with a bounded Lipschitz norm less than or equal than 1, right? And you can notice that this function applied to the process bt plus t eta epsilon, and this function applied to the process bt, because the Lipschitz constant in 1 is 1, and this second term is uniformly bounded by epsilon, this is less than epsilon. Okay, so as a result, when you take expectation of the first term, right, it converges to the expectation of the second term when epsilon goes to 0. And so this proves the convergence that we want. Okay, and so as our first application, we prove the following theorem. Here we'll prove the analog of the previous result only for the Brownian bridge. So we'll consider the supremum of the Brownian bridge now on the interval 0, 1. And we'll compute its distribution by showing that probability that it exceeds some positive b is equal to e to the minus 2b squared. Okay, and the proof goes as follows. Well, let me write the probability here that we want to compute as probability that there exists a time up to 1 such that the Brownian motion at that time it's level b. Okay, we could also write it using the stopping time, but first I want to rewrite this probability in terms of the specific representation of the Brownian bridge as a Brownian motion minus t w1. So this is the probability that this process, it's level b somewhere on the interval 0, 1. And now we will use this observation from the previous lemma that this process is independent of w1. So if I include the event in terms of w1, so for example, if I add the event that w1 is less than or equal than epsilon, then actually if you can write this as a product of two probabilities. So if you divide by the probability that w1 is less than or equal than epsilon, these factors will cancel out. And now let's write this as numerator over denominator. And in the numerator, let's notice that if we rewrite this first equation as wt equals to b plus t w1, the fact that we intersect with the event that w1 is less than epsilon means that this wt here can be squeezed in between b plus epsilon and b minus epsilon. So in particular, the probability in the numerator, okay, can be bounded from two sides by saying that there exists a t on the interval 0, 1 such that wt crosses level b plus epsilon, okay, intersected with w1 less than epsilon, and on the other side, probability that there exists t where wt is b minus epsilon, again intersected with the event that W1 is less than or equal than epsilon. And now we can rewrite these two probabilities on both sides using the reflection principle as follows. Okay, so for the first probability, it says that the following event happens. Okay, namely, if we consider this level b plus epsilon, our Brownian motion hits this time before 1. So, in other words, this first stopping time that we denoted t b plus epsilon, or the hitting time of this level, occurs before time 1. Okay, and the second part of the probability says that if you consider these levels plus and minus epsilon here, plus minus epsilon, then the process at time 1 ends up in this interval near 0. Okay, so in other words, this event occurs that the process ends up near 0 at time 1. Right, and we are going to use the reflection principle by reflecting the increment after this stopping time, which will result in the following picture. Okay, so our process should look like this, and then on this side it should end up in the interval between 2b plus epsilon, 2b plus 3 epsilon. And so by reflection principle, the probability on the left hand side can be written as the probability that this heating time of b plus epsilon occurs before 1, and then at time 1 the Brownian bridge ends up in the interval 2b plus epsilon, 2b plus 3 epsilon. And as before, now we can erase this first event here, because knowing that our Brownian bridge ends up in the interval 2b plus epsilon, 2b plus 3 epsilon at time 1, by continuity it has to cross the level b plus epsilon before 1. And similarly, the probability on the right hand side, you only replace b plus epsilon by b minus epsilon, so the same consideration will give you that this is the same as the probability that at time 1 you end up between 2b minus 3 epsilon, 2b minus epsilon. But then if we look at the ratio, so for example for the lower bound you have to consider the ratio of this probability divided by the probability that W1 is between minus epsilon and epsilon. Okay, when you let epsilon go to 0, right, of course, if you represent this probability as an integral of the density, and the interval is in both cases of size 2 epsilon, right, when you let epsilon go to 0, you end up by L'Hopital's rule, for example, with the ratio of two densities, right? And if you consider the standard Gaussian density at 2b and then divide it by the density, standard Gaussian density at 0, you end up with e to the minus 2b squared, and that's exactly what we were trying to prove. Okay, so in our next application, we'll compute the so-called Kalmagorov-Smirnov distribution. Okay, for the supremum of the Brownian motion with absolute value. So in other words, the difference with the previous result, that when we take a supremum on 0, 1, we take Brownian motion with absolute value. Okay, and we want to calculate the probability that this exceeds positive level b, and the so-called Kalmagorov-Smirnov distribution will be 2 times the series minus 1 to the n minus 1, so it's alternating series of exponential minus 2n squared b squared. Okay, so the proof goes as follows. So this probability on the left-hand side that we want to calculate, another way to write this is that either the heating time of B will be less than or equal than 1, or the heating time of level minus B will be less than or equal than 1. Okay, where here we define the heating time, since our time only goes up to 1, right? If it occurs on the interval 0, 1, then it's the first time, otherwise you can say it's plus infinity. And so, because of the absolute value, we want either of these events to occur. Now we are going to split this event into two pieces, depending on whether you hit B first, so if this time is less than this time, and in this case it occurs before time 1, okay, or the other way around, that minus B is less than heating time of B, right? And then you only need to mention that this occurs before time 1, right? And by symmetry of the process, both probabilities are equal. If you just put the minus sign in front of your Brownian motion, one event will turn into the other, so this is just twice, let's say, the first probability. Okay, this is the probability that you hit B before minus B, and then the fact that this occurs before time 1, I will simply write this as follows, that there exists some time t before 1 or up to 1 such that the process at that time is equal to B. Okay, we can also write this as probability that tau B is strictly less than tau minus B intersected with the event A1, where in this proof we'll consider the following sequence of events. So by AN we'll write the fact that there exists a sequence of times T1, Tn on our interval 0, 1, such that the Brownian bridge at those times takes values minus 1 to the j minus 1 times b. Okay, in other words, at time 1 it takes value b, at some later time it takes value minus b, and so on alternatingly. Okay, so A1 just means it takes value b at some point of time. And then let's write the above probability as the probability of A1 minus the probability of A1 with the complement of the event that tau b is strictly less. So in other words, now tau minus b will be strictly less than tau b. Okay, and what happens in the second probability can be visualized as follows. Okay, we have our two levels, plus b and minus b, and then we know that at some point before 1 our process takes value plus b, but at the same time it must hit minus b before it hits b. So actually this means that something of this form must occur. So there will be a stopping time tau minus b occurring first, and then at some later time before 1 you cross b. Okay, but then by symmetry of the process we can rewrite this as follows. Okay, again we have two levels b and minus b, and if we put minus sign in front of our Brownian bridge, then it means that we must hit b first, and then at some point of time before 1 we hit minus b. So in particular, this second term, this second probability, A1 intersected with this event here, okay, just by symmetry, it's the same as probability that you hit plus B first. Okay, but the difference that now we know that on the interval 0, 1, there is a pair of times where at time t1 you hit B first, and at a later time you hit minus B. So now we have a pair of times, so in particular, this is what we call event A2, right? Once you flip this picture by symmetry, now you have a pair of times t1, t2. Okay, but notice that this last probability is exactly like the probability that we started with, except A1 is replaced by A2. Okay, so by induction we can proceed in exactly the same way with A2, A3, and so on. So more precisely, what we just did can be done for the probability that B is hit first, and you have the event AN, right? You can rewrite this as probability of AN minus the probability of AN on the complement. So in other words, minus B is hit first. Okay, and then for the second event, if you flip it by symmetry, you can see that it will mean that B is hit first, and you have one extra point in the event. So in other words, event A and minus 1 occurs. Okay, and so by induction, the probability that we started with, namely the probability of A1 intersected with this event, can be written as a probability of A1 minus probability of A2, and so on. So you have this alternating series. Okay, and if you stop at n, okay, the last event will be probability that tau b is before tau minus b, a n plus 1. And once we now calculate the probability of an and see that it goes to 0, when you let n go to infinity here, you just end up with that alternating series. So what remains now is to calculate the probability of this event an. Okay, and this is where we'll use the reflection principle and this point of view of a pin-down Brownian motion. Now, the event an was written for the Brownian bridge, but now let's write the Brownian bridge explicitly in terms of the Brownian motion as before, and redefine this event, of course, in terms of the Brownian motion. So in other words, there exists times tau t1, tn up to 1, such that this w tj minus tj w of 1 takes value minus 1 to the j minus 1 times b. And so this probability is now rewritten in terms of the Brownian motion. And here again we use the fact that this Brownian bridge here is independent of w1. So we can write this as probability of an intersected with the probability that w1 is less than or equal than epsilon divided by the probability that w1 less than or equal than epsilon, and then try to see what happens when epsilon goes to 0. Okay, so in particular, let's try to visualize the event in the numerator here. Okay, and the event in the numerator can be visualized as follows. So we have two levels, plus b and minus b, and we know that at some time we hit b, and then there is a later time when we hit minus b, then there is a time when we hit b again, and so on. And then at time 1 we end up at 0. So there is a level 0 here, and we end up within plus minus epsilon from 0 at time 1. Okay, in particular because in this event we say that this time 1 we hit b. Okay, without loss of generality, we can pretend that this is the stopping time, which is the heating time of B. Okay, so we know that the stopping time B occurs before 1, and then at a later time, your process has to go to minus B, and then go to plus B again, and so on. And then at the end, it should end up near 0 like this. Okay, and then we apply the reflection principle to this stopping time given by tau beta. Okay, and then if we reflect the increment of the process after this time around this line B, that means that we have another level here given by 3B. And so the reflection means that at some time after the stopping time you end up at 3B, then you come back to B, and so on. And then in the end, the level 0 after this reflection will become 2B. So here you have 2B, and then you are within plus minus epsilon of 2B. So your process in the end ends up here. Okay, and what this means is that the event in the numerator by this reflection principle can be rewritten by saying that at some time before 1, our process at that time, so that time here is tau 2. So here, you see, we have to hit level 3B before 1. So, and that happens on this picture, it corresponds to what we called T2 before. Right, so at some time T2, you have to hit level 3B. Then at some later time T3, you have to come back to level B, and so on. And then in the end, the level 0 was reflected to 2B, right? That means that W1 should end up in 2B minus epsilon, 2B plus epsilon. Right? So the probability in the numerator is the same as the probability of this event here, that this sequence of time exists. And notice that we don't need to mention the time t1 anymore, that at some point you hit B, because the fact that you hit 3B by continuity of the process means that you had to cross B. So this fact that tau B was less than 1, it's automatically included in this event. In other words, by this reflection principle, we eliminated one time in our event. So now we have only times t2 up to t3, and then the final time 1, what happens at time 1. Okay, and then if you keep repeating this, so next you have this time tau 3b. If you reflect the process after that and you continue doing this and keep track of what's going on, in the end you'll see that once all the times are eliminated, you will end up with the event that the process at time 1 is within plus minus epsilon of 2nb. Okay, and then remember, this was just reflection principle applied repeatedly to the numerator, and our denominator was the same, that you are within epsilon of 0. Okay, I'm just not writing that you are within plus minus epsilon of these values here, but then when you let epsilon go to 0, again, the ratio will be just the ratio of the densities, and so you end up with e to the minus 1/2 2nb squared, which is exactly this term e to the minus 2n squared b squared that we get in the telescopic series in the Kalmagorov Smirnov distribution. Okay, and so this finishes the proof. Now there is a couple more results in the notes which I'm not going to go over here because it's exactly the same calculations. So first there is a generalization to a two-sided boundary of this last lemma. Namely, you can also compute the probability that at some times before 1 you will hit either level minus A or B, or level plus B. So in the previous lemma this was minus B and B, but now you just want to know what's the probability that you hit not necessarily symmetric boundaries above and below 0. Okay, it will be essentially the same calculation, and you will also get some alternating series. Okay, but again, I'll refer to the notes for that, and then once you have this result, you can also compute the distribution of the spread. Okay, namely, you can compute the distribution of the difference of the supremum of the Brownian bridge minus the infimum of the Brownian bridge on the interval 0, 1. Okay, and it's just a straightforward calculation once you have this two-sided boundary. Then finally, let me say a couple of words about the Kalmagorov-Smirnov test. Okay, since it was our motivation in the previous section, let's recall that we considered the situation when we are given a sequence of IID random variables and they come from some distribution with a continuous CDF. Okay, then in the last section we proved that if you consider the following quantity, you take a supremum over T of the empirical CDF minus the CDF, and we had some scaling by square root of n. So we showed that this distribution is independent of f as long as it's continuous of this CDF, and then because of the convergence of this empirical distribution to a Brownian bridge, right, we showed that the distribution of this supremum converges to the distribution of the supremum of the absolute value of the Brownian motion. Okay, and in this section we proved that this supremum is, its distribution is given by this Kalmagorov-Smirnov distribution. Okay, so we computed this limiting distributions precisely. And the Kalmagorov-Smirnov test is a test whether your data, your points xi, indeed come from the distribution with a given CDF. Okay, and if this CDF is the correct one, then you have this convergence distribution. But otherwise, okay, if here in the supremum you are subtracting the wrong function, then the difference will not go to 0. And after scaling by square root of n, you know, this supremum will go to plus infinity, right, if you subtracted the wrong function. So as a result, the test is based on checking whether the value of this dn, this statistic dn, is too big. And so you just have to decide what too big means, right? So if you subtracted the correct CDF, then the probability that dn exceeds some level, okay, converges when n goes to infinity to this Kalmagorov-Smirnov distribution on the interval from c to infinity. Then you pick some number alpha, which is called the level of significance in statistics, okay, which represents what do you mean by unlikely, or in other words, how small this probability should be for you to consider the values of this statistic to be unusually large, right? So of course it depends on the situation, but canonical choice of alpha is 0.05. And once you, so given a level of significance that you choose in advance, you compute the value of this c by looking at the Kalmagorov-Smirnov distribution, right? And then your Kalmagorov-Smirnov test or your decision rule states that if dn exceeds this level, then you consider the value of dn to be unusually large, and you conclude that the function f is not the correct CDF. Okay, but otherwise, if dn is below this level, you conclude that a given function f is the correct CDF. Okay, and I don't justify the statistics reasoning here in enough detail, but the main point is that this result is indeed based on the results of this section and the previous section. So it uses the convergence of empirical process to the Brownian bridge, and also for this test we need to calculate the distribution of the supremum of the absolute value of the Brownian bridge, which we did in this section.